I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the 2024 exams FRQs for AP Physics 1. This question is question 1. Today we're going to be talking about the AP Physics 1 2024 FRQs. Today we're going to talk about FRQ 1. So in this case, we have a block that is moving along this path with this ramp. It says it has a mass of m and it starts a height of 6r above the horizontal. And it goes through a couple loops and it reaches those circular loops at points B and C at the very top of the loop. It also tells us that it does not leave contact with the track. So if it doesn't leave contact with the track, that means it has to be moving at points B and C in order to make it around and to maintain contact with the track. It also tells us that their friction forces are negligible. So that means that energy is going to be conserved through this whole process. Also, we look at the picture and we think that the topics that we're going to use, and obviously conservation of energy because it's an energy bar chart, and circular motion would be another concept that we'd be looking at. So diagram A shows an energy bar chart, and it represents the gravitational potential energy of the block Earth system and the kinetic energy of the block at point A. So when the block is released from a height at rest of 6r, so thus we have no kinetic energy at the for diagram A. But notice we have a height of 6r, and the height of our bar for UG is 6 as well. It gives us some more information, and it tells us that we're going to be drawing part B or diagram B for our energy bar chart. So some information tells us is the height is 2r at B, which is just going to be the diameter, and it tells us that the magnitude has to be drawn compared to the scale in diagram A. Well, we just noticed that the height was 6 for a 6r, so for 2r we should have a height of 2 for UG. So we're going to go ahead and draw a bar that has a height of 2. Now, it also told us in the problem that all friction forces are negligible. If friction is negligible, that means energy is conserved. So if energy is conserved, we started with a total height of 6, that means we have to end with a total height of 6. So if we have 2 for UG, that means the remaining amount of energy has to be kinetic energy, and we're going to draw that a height of 4. So here's our energy bar chart showing conservation of energy. Since there's no frictional forces, there's no work done to take energy out or transfer energy in. So the total height for the mechanical energy is 6 in both situations. So part B asks us to derive an expression for the speed of the block, starting with conservation of energy. Well, we're going to use our bar chart, and we know that UG at point A is going to equal UG at point B plus the kinetic at point B, as our bar chart indicates. And then we're going to substitute the equations in, putting subscripts for delta y of A and delta y for B in the second situation, and the velocity at point B, we put a subscript of B. So what's consistent in each of these is the fact that each term has mass. So the reason it doesn't ask for mass in our answers, just terms of r and physical constants, which is going to be little g, is because the mass is going to cancel out. So we don't need to use the mass in our final equation. So now we can substitute in the heights that are given. So delta y A is 6r, delta yb is 2r, and we simplify our equation. Now we can go ahead and work through and solve for the velocity at point B by subtracting the g2r over to the left. And that's going to give us an equation that 4gr equals 1/2 vb squared. Continue with our algebra, multiply both sides by 2. That's going to give us the vb squared equals 8gr. Then take the square root of both sides, and we can simplify that by taking out a square root of 4 and making it 2 root 2gr, or you can leave it as the square root of 8gr, which should get you full credit because it's an algebraic equivalent to the final answer. Part C asks us at point C, we want to draw all forces that are acting on the block, starting with a vector starting on the dot from point C and pointing away from the dot. So each force has to be its own vector. This is key. So when we draw gravity, we know gravity points straight down, so you can label it mg, fg, force of gravity, anything that says that it's the force of gravity that's acting on it. Now, the block is oriented upside down at point C. So since it's upside down, the track is above it. So if the track is above it, that means that the track is going to be pushing down as well. So the normal force that we draw, because it doesn't leave contact with the track, is what it gave us in the description. The normal force is also going to be pointing down. So we're going to draw the normal force starting from the dot and pointing away from the dot, so that it ends up with two distinct vectors. So you can't draw one vector and call it two things. You have to draw two distinct vectors for each individual force starting on the dot and pointing away. So this is the free body diagram for point C. The length of the vectors, you could draw mg shorter, longer, doesn't really matter. What matters is that you have the force values. I happen to draw them the same length, which doesn't matter. All that matters is that you drew the values of each of the forces. Part C2, a student claims that the block can start at a height of 4m and still make it around point C without losing contact with the track. Explain why this claim is incorrect. So we know that if it's reaching a point of C, that is also a height of 4r, because we've got the track as a height of 2r above the ground level, and C is radius is r, so that makes the diameter 2r, so it's a total of 4r. So they both start and end at a height of 4r, which means that the UG at both points is going to be the same. Well, if the UG is the same and energy is conserved, that means that there's no energy left for kinetic energy. So that means we'd have zero kinetic energy. If you don't have kinetic energy, that means it's not going to be moving at point C. So that means if it's not moving at that point, then it would lose contact with the track or just not make it around. So it's going to have a velocity that's greater than zero to make it around the loop. So it would have to start from a height higher than 4r in order to make it around the loop. So we can actually figure out the exact velocity that it would need, and this was not asked, but this is just a side note. So the smallest value for our normal force we can have is 0, meaning that it's still barely in contact with the track. So the minimum net force would be mg, and we can use our second law equation, substituting a as v squared over r, and then we can solve for the velocity. The masses would cancel out, and we end up with v squared equals gr. So that means at minimum, the speed at point C would have to be the square root of gr, but because it's a higher height at that point, it would have to be moving a little bit faster through point B. That's have to be faster than square root of gr at point B than at point C. So that's the minimum velocity at point C. So this is 2024 FRQ1. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.